In this video tutorial, we will discuss physical and chemical changes, counting atoms, and balancing equations. Alright, let's do a brief review of grade 9 science, physical versus chemical change. When we talk about physical changes, we are referring to those that affect the appearance of a substance but not its chemical composition. So ice, liquid water, and steam look very different from each other. But in all three cases, we have the same particle, H2O, the water molecule. So they may look different physically, but chemically they are identical. So when we talk about phase changes, going from a solid to a liquid or liquid to gas or anywhere in between, we are talking about the same chemical composition. We're only changing the distance between the particles themselves. And so all phase changes are physical changes. When we dissolve a substance, so we dump a lump of sugar into water, the water molecules start to spread out the sugar. In the end, sugar tastes sweet. Sugar water also tastes sweet because the molecule structure has not changed. They are still sugar molecules, just surrounded by water molecules. The water remains as H2O, and the sugar stays as C12H22O11. So again, the only thing that changes here is the distance between the particles. The chemical composition remains unchanged. So dissolving is still a physical change. Pounding, scraping, stretching, ripping, denting, cutting. These all change the appearance of a substance, but they do not change the particle itself. So when I tear up a piece of paper, it's still paper particles. It's still paper molecules. I didn't break up those chemical bonds. I didn't make something new. Because that would be a chemical change, where a new substance with a different chemical composition is created. So for example, electrolysis of water. If I apply an electrical voltage to water, I can separate the water molecules, H2O, into its component elements, oxygen and hydrogen. So I've gone from one type of particle, H2O, to two types of particles, O2 and H2. Now during this electrolysis process, I know that this side is the hydrogen side and this side is filled with oxygen gas. I can tell that because, take a look at the formula, H2O, 2 parts H, 1 part O. There's always twice as much hydrogen as there is oxygen. So just looking at the volume, I can see that there's twice as much gas here than there is over here. So this must be the hydrogen side, this must be the oxygen side. Meanwhile at the bottom, we have water molecules. Now, what proof is there that the gases produced during electrolysis are no longer water molecules? Because when I add electrical energy to water, I make gas, but when I add heat or thermal energy to water, I also make a gas. How do I know that this gas is still H2O, while these gases are no longer H2O? Well, we can test out their properties. So for instance, if I had a glowing splint, so a piece of wood that is just glowing, it's not on fire, but it's just glowing, and I dip it into pure oxygen. Well, of course, fire needs oxygen. By dipping it in, this piece of this glowing splint will burst into flames again. But if I tried to do that in steam, I'm pretty sure the glowing splint would not burst into flames. If anything, it would probably go out. So oxygen and steam have two different properties. You put a glowing splint into oxygen, it will burst into flames. You put it into water that is gaseous, so steam, it will not. Two different properties, therefore it must be two different substances. Now, if you try to put a flaming splint into hydrogen, the hydrogen will explode, making a popping sound. But if you put a flaming splint into the steam, it's going to go out. Once again, two different properties for two different substances. So to help you determine if a new substance has been created, these are a few signs you should look out for that may indicate that a chemical change has occurred. So if you have energy being released or absorbed, so like when you're burning something, we call that a combustion reaction, or maybe a cold pack that we use for first aid scenarios, it absorbs energy so it feels cold. Or if there's gas being produced, a new color change, or the formation of a precipitate, which is a solid that appears from a liquid. So here we have two liquids mixing together to form a solid powder. Though any one of those signs can indicate that a chemical change has occurred, the one question you must ask yourself is, has a new substance been created? So just because I have a color change doesn't mean a new substance has been created. So take for instance, let's say I had some grape juice. Then I added some more water to it and now it's not as sweet. Then I added even more water to it because I'm a monster. And now it doesn't even taste like grape juice, it just tastes like water at this point. Well, have I changed the molecules? No, it's still just grape juice. It's just being more dilute, more spread out. So even though it has a color change, it's still not a new substance. So in the end, you have to ask yourself, did I make a new substance? All right, so what I want you to do is classify each of these changes as either being physical or chemical. Give it a try. When you're ready, press play, and we'll take it up together. All right, so water turning to ice is going to be a physical change because it's still H2O, still H2O. Wood being burned is definitely a chemical change. The smoke that comes out and the ashes that are left over after the wood has been burned are definitely two different substances than what the wood originally was. Iron turning to rust is also a chemical change. While iron is strong, rust is very brittle. Two different substances, two different properties. Sugar added to water is a physical change. That's just dissolving something. No new molecules are created. Copper metal being bent into a different shape is still just a physical change because it's still copper metal. No new properties there. Water separating into hydrogen and oxygen gas is definitely chemical change. While aluminum pop can that is warmed above a stove is just a physical change. It is still made up of aluminum atoms. Finally, mixing vinegar and baking soda is a chemical change. This is the typical science fair experiment that elementary students conduct as a volcano demonstration because it creates a fizzy gas, in this case carbon dioxide. So a new substance is created. So this should be a review from grade 9, how to count atoms. Let's briefly review over some of the rules you would have learned. First, the symbol of an element represents one atom of the element. So there's no need to put a 1 there. This is automatically assumed to be one atom of sodium. On the other hand, a subscript is a number written in the lower right-hand corner behind the symbol of an element. If there's more than one atom of the element, then a subscript is used to indicate the number of atoms present. So here we have 2 atoms of hydrogen. Now if you have a subscript outside a bracket, it multiplies all the elements inside the bracket. So this bracketed area shows that these groupings of atoms are stuck together. We call this a phosphate ion. So there are 2 of these phosphate ions, these PO4s. So when you look at that, 1p, 2p, altogether 2 phosphorus. 4 plus 4, altogether 8 oxygen. Or if you'd like, just multiply the 2 into the bracket. So 2 times 1 equals to 2 phosphorus. 2 times 4 equals to 8 oxygens. And of course, there's only 3 magnesiums. While these smaller numbers are called subscripts, the bigger numbers in front of the element is called a coefficient. All right, so this number is in front of the chemical symbol and indicates the number of atoms of that element. So we have 3 atoms of carbon. But more importantly to us, a coefficient also multiplies the number of atoms of each element in the entire formula. So over here, so this is saying we have 2 water molecules, H2O, H2O. While this one's saying we have 3 copper 2 sulfates, so 3 of these CuSO4s. Now a lot of students have difficulty recognizing what the difference is between a subscript and a coefficient. So when you look at these 2 scenarios, they both seem to tell you the same thing. 2 hydrogens, 2 oxygens. Well, this 2 multiplies everything in the back, so that's 2 times H, 2 hydrogens, 2 times O, 2 oxygens. So what's the difference? Well, H2O2 says I have 1 molecule of H2O2. They're all chemically combined together into one giant molecule. While 2HO says that I have 2 of these hydroxide ions, so the HO and the HO. Some of you might still be confused, so let me draw you a picture that might make more sense to you. Saying 2HO is like saying I have 2 Big Macs, while 1 H2O2 is like saying I have 1 McHeart Attack. In both cases, you have the same number of ingredients, 4 buns, 4 buns, 4 patties, 4 patties, and 2 of those inner buns, and whatever they're called. But same number of ingredients, same thing, same number of atoms, 2 H's, 2 H's, 2 O's, 2 O's, but the subscripts and coefficients tell you a different story of how they are assembled. So subscripts tell you how to make your molecule. So how do you assemble this monstrosity? While coefficients tell you how many of these molecules to create. So how many of these burgers will you create? Alright, so subscripts tell you how to assemble it, coefficients tell you how many to create. So going back here, I recommend you ignore the coefficient first and just count how many atoms are in each of these molecules. In this case, there are 2 hydrogens and 1 oxygen. But since you want to make 2 of these water molecules, you want to multiply your recipe by 2, and now you have 4 hydrogens and 2 oxygens. Now I know some of you think you can do it all in one step, and you probably could, absolutely, for the easier ones. But for the more complicated ones, like you'll see on the other page, even I will still ignore the coefficient first, calculate how many there are in just one molecule, and then multiply by the coefficient afterwards. It's better to do it in 2 steps, take a little extra time, be a little more careful, and then you're less likely to make a silly mistake. I personally would prefer to take an extra 2 seconds to guarantee my mark than to save that extra 2 seconds and then lose it in a silly mistake. Alright, so I have 1 copper, 1 sulfur, and 4 oxygens in this compound. But since I want to make 3 of these, I'm going to multiply everything by 3, giving me 3 coppers, 3 sulfurs, and 12 oxygens in the end. Again, I'm going to ignore the coefficient. I have 1 lead. Now, there's a bracket over here, so there's 2 of these NO3s, so I'm going to multiply it in. Means I've got 2 nitrogens and 6 oxygens. But now I want to make 4 of these, so I'm going to multiply everything times 4, giving me 4 leads, 8 nitrogens, and 24 oxygens. So what I'd like you to do now is press pause, try this out yourself. When you're ready, press play, and we'll take it up together. Alright, and here are your answers. The only ones that you might have difficulty with is over here. You'll notice that the hydrogens were split up into 2 different areas, H4 here and H3 here. You must combine them together to make 7 H's. Now there is a reason why they separate these H's, is because this is a polyatomic ion and this is a different polyatomic ion, but you'll learn more about that one in grade 11. You might also need some help with these ones over here. So what I've done again was calculate just by itself without the coefficient, 1 barium, 2 chlorines, then realize I need to make 3 of these barium chlorides, so I multiply everything by 3, and that's what I've got. Alright, so this one over here says I have 2 atoms, types of atoms anyway, 1 barium type and 1 chlorine type, so there's 2 types altogether, but I have 9 atoms altogether because 3 of them are bariums, 6 are chlorines, add them up, you get a 9. I did the same thing down here. First I calculate how many aluminum atoms by itself without the coefficient, same with the carbon and the oxygen. There are 3 types of atoms, aluminum, carbon, and oxygen. Then there are 4 aluminum carbonates that I want to make altogether, so I multiply everything by 4, giving you these values with a total number of atoms of 56. Finally down here, exact same thing. There are 4 types of atoms, nitrogen, hydrogen, chromium, and oxygen. Then I calculate it by itself, how many of each type there were. Since I'm making 2 of these compounds altogether, multiply everything by 2, get these final values as well. During a chemical change, atoms are neither created nor destroyed. They're only rearranged into a new substance. This is known as the law of conservation of mass, because the mass of the reactants going into a chemical reaction is equal to the mass of the products coming out of the chemical reaction. Now, chemical reactions can be represented on paper through the use of chemical equations. So the first type of chemical equation is called a word equation. This describes a reaction through words. So for instance, hydrogen gas reacts with oxygen gas to produce liquid water. Alright, so this plus symbol means that these chemicals are reacting, while the arrow shows that they are being produced. However, the textbook may use the term yields, alright, but produce and yields are the same thing. Now, reactants are generally written on the left side of the arrow, so this is what you'll start with, while products are on the right side of the arrow, what you end up with. So this is what the chemicals look like before the chemical reaction, and this is what they look like after the chemical reaction. Now, instead of using words to describe the chemical reaction, we can make things quicker by writing out their chemical symbols instead. This is known as a skeleton equation. Now, these symbols down here represent the state of matter for the particular element or compound. S stands for solid, G stands for gas, L stands for liquid, while AQ stands for aqueous solution, meaning that it was dissolved in water. So it's not good enough just to tell the reader that hydrogen plus oxygen makes water. You must tell the reader that hydrogen gas reacts with oxygen gas to produce liquid water. The states of matter matter. Now you may have noticed that I wrote hydrogen as H2 and not just H. I wrote oxygen as O2, not just O. This is because hydrogen and oxygen are diatomic elements. These are elements that are unstable on their own, so in their monatomic state, mono meaning one, atomic meaning atom, so single atom state, and they must always be bonded with another atom. If a different element is unavailable for bonding, they will bond amongst themselves. So you must never write these 7 diatomic elements on their own. You'll never see it just as H or O or F, Br, I, N, Cl on their own. They'll always be H2, O2, F2, Br2, I2, N2, Cl2. They must be bonded with either a different element or themselves. To help you remember these 7 diatomic elements, there is a small trick you can use. Because there are 7 of them, starting with element number 7, nitrogen, they make a 7. So nitrogen, oxygen, fluorine, chlorine, bromine, iodine, they are all diatomic elements. But don't forget hydrogen as well. So there you have it, the 7 diatomic elements, making the number 7, starting from number 7, just don't forget hydrogen. Now, truth be told, most students do not use that small trick to memorize the 7 diatomic elements. Instead, they just shove all the letters together into one giant word, Hofbrinkel. Hofbrinkel. Some students use Brinkel-Hof, but most will use Hofbrinkel. Regardless, do whatever works for you. Now, so far we have looked at word equations and skeleton equations, but there's a problem with the skeleton equation. The law of conservation of mass states that atoms are not created and they're not destroyed during a chemical reaction. So the atoms going into reaction must be the same atoms coming out of the reaction. They're just being rearranged. But when we look at the skeleton equation, we see there are 2 hydrogens going into the reaction, 2 hydrogens coming out of the reaction. So far so good. But 2 oxygens going into the reaction while only 1 comes out. That's not allowed. Atoms don't just mysteriously disappear and they don't get destroyed. And that's why we need the balanced equation. By adding in coefficients, we balance the equation so the number of atoms going into the reaction are the same number of atoms that come out of the reaction. Thus, the law of conservation of mass is upheld. By putting a 2 here, we now have 4 hydrogens and 2 oxygens. And then by putting a 2 here, we now have 4 hydrogens and 2 oxygens. So the number of atoms going into the reaction is equal to the number of atoms coming out of the reaction. Mass going in equals mass going out. Mass is conserved. Now here are some hints we can use to help us balance the equation. First, I'd like to set up a T-chart that summarizes the number of atoms of each element on either side of the equation. So I call it a T-chart because it looks like a T. Now start by balancing all the atoms except for hydrogen and oxygen. Try to leave these atoms for last. It won't always work, but 9 times out of 10 it's a good way to start the balancing process. So first I'm going to write out how many atoms of each element are present. 2 irons, 3 oxygens, 1 carbon on the reactant side, the left side. 1 iron, 2 oxygens, and 1 carbon on the product side, the right side. Obviously this is not balanced yet. The number of oxygens don't match up and the number of irons don't match up. So the hint says to balance everything except for hydrogen and oxygen, leave those for last. So let's do that. Now when you're balancing equations, you can only play around with the coefficients. You're not allowed to play around with the subscripts. Watch what happens if I mess around with the subscripts. So oxygen has a valence charge of 2-, while iron has 2 options, 2+ or 3+. In order for this compound to exist, in order for the valence charges to zero sum, it cannot be iron 2+. Because 2 of the 2 pluses added to 3 of these 2 minuses does not add up to 0. We're missing electrons. But if iron was a 3+, and we have 2 of them, now 6 positive, 6 negative does add up to 0. And so, each electron lost has found a new home. Now watch what happens when a student messes up with the subscripts. Oh, this is not balanced. I should have 1 iron. So I'm going to scratch this out and just make it a 1 iron. I want only 2 oxygens, so I'm going to scratch this out and make this a 2. So now my equation is FeO2 and everything is balanced. Success! No, it's not. Watch what happens when you try to zero sum this chemical formula. 1 iron worth 3+, 2 oxygens each worth a 2-, do not add up to 0. I don't have enough electrons to make this stable. If this is unstable, it doesn't exist. If it doesn't exist, your marks don't exist. So don't mess around with these subscripts. Doing so will change the chemical formula into something that might not exist. Alright, so let's do this properly by only playing around with the coefficients. I want to balance out my iron atoms, but I can't change this number, so I must change this number over here. Instead of 1 iron, let's make it 2. So I'm going to write a 2 over here, but as soon as I do this, I need to recalculate the number of atoms on this side. I now have 2 atoms of iron. Now my recommendation is for you to cross out the numbers and put in a new one. Don't just erase all the old ones and then put in the new one over here. I find it extremely messy when students keep using the eraser back and forth, and sometimes they use the eraser so much that they rip a hole through the paper. But more importantly, this shows you a history of what you've been doing so far. So if you need to backtrack, you don't have to go all the way to the beginning and start all over again. You can just backtrack 1 step, 2 steps, however many steps you need to go in order to figure out where you might have gone wrong. Now the final reason why I want you to cancel things out instead of just erasing, if you end up canceling 1 whole row of numbers, then 2 rows, then 3 rows on both sides, and it's still not balanced, chances are you've done something wrong. There is no equation in our course that requires you to cancel out 6 columns and starting on a 7th column. At that point, you've probably done something wrong. Likely, you've made a calculation error where you added up the atoms incorrectly, or, and this happens quite a bit, you may have copied the question incorrectly. And by copying the question incorrectly, there might not even be an answer for that one. So in such instances where you've canceled 6 whole columns and you're starting a 7th one, I would recommend that you start all over again. Start over again by checking to make sure you wrote the question correctly and that you're doing your math properly, you're counting the atoms properly. Because chances are one of those 2 mistakes will correct whatever issue you're having. I would say 99% of the time in this course. Okay, so now my irons are balanced and my carbons are balanced. All that's left is the oxygen. As I mentioned before, if you see a 2 and a 3, you should be thinking of the number 6 because 6 is the lowest common multiple between the 2 numbers. So how can I get 6 oxygens on the reactant side? I can't play around the subscript, I can only play at the front, so therefore I need to put a 2. And in so doing, I need to recalculate again. Now how many irons do I have? 2 times 2 is 4, so I have 4 irons. And now I have 2 times 3, 6 oxygens. Now I've messed up my irons, they're no longer balanced, no big deal. Things usually look their ugliest just before the equations balance out. Let's just focus on the oxygen on this side now. So again, I can't play with the subscript, I can only play with the number in the front. What can I put in front of here to get 6 oxygens? Well, the answer is 3. 3 times C equals 3 carbons, and 3 times 2 is 6 oxygens. Now I've really messed up my irons, really messed up my carbons. It feels like it's not worth it, but don't fret, it is fine. To get 3 carbons over here, what number should I put in? 3. So let's recalculate, and we got a 3. So now that our carbons are balanced again, our oxygens are balanced again, now I need to balance out my irons. Instead of having a 2 here, I need to have 4. So what number can I put in here to make this a 4? 4. We can now recalculate and see that our atoms are balanced. Alright, so quite often it will get pretty ugly right before it works out. Just be aware, if it gets super ugly and you've canceled out 6 columns and you start on the 7th, chances are you've done something wrong. That's when you need to restart all over again. Now you'll notice I like to write the number first and then recalculate down here. I don't like to cancel things out and then write it up here. It doesn't seem like much of a difference, but this is one way to prevent the most common silly mistakes students make. Let's repeat the step by going the other way around. I have 1 carbon, but I need 3, so I need to put a 3 up here. I want you to put the 3 up here first before you cancel out. Because if you cancel out first, psychologically, as soon as you see this, you go, oh, I'm done! And students move on to the next question without actually putting the answer up top. Silly mistake. Easily avoidable. Put the number up top first, and then you're forced to recalculate, and then now you can check to see if it matches up. Alright? There's no premature victory with this method. But again, you do whatever you want, whatever you feel comfortable with. I'm just trying to show you the common silly mistakes that my students make, the ones that I see every single year. All right, moving ahead. Now this one's interesting. You'll notice that there are compound ions present. One of the hints that I gave you is that if a compound ion exists on both sides of the equation, must be both sides of the equation, you may wish to treat it as a single unit rather than splitting it up into its individual elements. So instead of separating the sulfate out into sulfur and oxygen, I can instead keep them as a unit because they didn't break up. Sulfates appeared on the left side, sulfates appear on the right side. As I mentioned in a previous lesson, polyatomic ions are very stable groups of atoms, and they rarely break up during a chemical reaction. Typically during a chemical reaction, they will react as a group. So if you're going to react them as a group, you might as well treat them and balance them as a group. And this saves you an extra step. Instead of having to balance two elements, sulfur and oxygen, you just balance one, sulfate. Now, some of you are asking, I see hydroxide on this side, but I don't see hydroxide on this side. How can you use hydroxide then? Well, here's another trick. Don't think of water as H2O. Try thinking of it as hydrogen hydroxide instead. It's still H2O, but now you've got that hydroxide to help you out. Now, you can't pull this trick for most other compounds, so you can't just randomly split them up wherever you want, but for water, you definitely can. Think of it as hydrogen hydroxide, and in fact, it is much easier to think of water as hydrogen hydroxide when we start talking about acids and bases. Alright, so let's set up our initial values. 2 hydrogens, 1 sulfate, 1 boron, and 3 of the hydroxides. Remember, this 3 outside the bracket means I have 3 of these OHs. Gotta multiply everything in. On the right hand side, we have only 1 hydrogen, okay, not 2, because this one belongs to the hydroxide now, so just 1 single hydrogen. We have 3 of the sulfates, because again, that subscript outside the bracket means there's 3 of these sulfate ions. We have 2 borons, and of course 1 hydroxide. Let's go back to our hint, leave oxygen and hydrogen for last. So let's balance out the sulfate. Again, I can't play around the subscripts, I can only play around the coefficients. I have 3 sulfates on the right, 1 sulfate on the left. Obviously I can't just delete this 3, that's a subscript, I can only play with coefficients, so I must play on this side instead. By putting a 3 here, I can recalculate. Don't erase, just cross it out, and we've got 3 sulfates, so that matches up. Let's look at the borons now. I have a 1 and a 2. Obviously I can't play with the subscript, so I'm going to play on this side instead. By putting a 2 here, I now have 2 borons. But don't forget this coefficient also affects the hydroxide, and now I have 6 of them. So the sulfates are balanced, the borons are balanced, but the hydroxides are not. I have 6 on this side, only 1 on this side, so let's put a number in front over here. Now I've got 6 hydroxides, so let's recalculate. But don't forget you also have 6 hydrogens as well. And now my hydrogens are the only ones that are left unbalanced. Sulfates are fine, borons are fine, hydroxides are fine. But have you noticed the mistake that I made earlier on? That's right, I purposely made this mistake, just to see if you were paying attention. If you look back over here at my history, I changed the 1 in front of the H2SO4 to a 3, but when I did so, I changed the sulfate, 3SO4s, but I did not recalculate for the hydrogens. In fact, there's actually 6 hydrogens here. So when I correct this mistake, we see that everything is fine now. The left side equals the right side. Alright, let's take a look at the last one down here. Alright, so let's count how many atoms are on each side initially. This one's a little trickier, but here we go. 4 carbons, 8 hydrogens, but 3 oxygens. You'll notice that both reactants have an oxygen atom inside of them. And that leads us to this hint. Sometimes an element may appear in more than one compound. Be mindful when adding these elements up. So that's where a lot of students will make their silly mistakes as well. Same on this side, 1 carbon, 2 hydrogens, but 3 oxygens. 2 from here, 1 from here. Alright, now as before, we leave oxygen and hydrogen for last. Let's start balancing with the carbons. Can't play around with the subscripts, I can only play around with the coefficients. So I'm going to put a number 4 here, and then recalculate. But don't forget, you're also changing the number of oxygens, because now there are not just 8, but 9. 8 from here, plus 1 equals 9. Now, should I balance my hydrogens next or my oxygens next? I recommend doing the hydrogens because oxygen is easy to balance by itself afterwards. If you just change this number, it affects no one else. But if you try to balance your hydrogen last, you change this number, it affects the hydrogen and the oxygen, so that's a double whammy. So I like to leave oxygen for last in this case. That way if I mess around with it, it only changes the oxygen. It doesn't affect anyone else. Okay, so I have 8 hydrogens on this side. I only have 2 on this side. So I'm going to put a 4 over here. I now have 8 hydrogens, so recalculate. But now I also have 4 oxygens here. 8 oxygens here equals to 12 oxygens over here. Now my carbons are balanced. My hydrogens are balanced. I just need to balance the oxygens. But there's a problem. I need to have 12 oxygens. So if I put a 6 over here, I now have 12, but don't forget this guy, I actually have 13 oxygens. So that's no good. Let's go 1 below this, make it a 5. So that makes 10 oxygens here, plus 1 equals 11. So I keep missing the target. I'm always off by 1, either too high by 1 or too low by 1. But I don't want to play around with these numbers because then I would mess up my carbons and my hydrogens. So here's a little trick you can do in this specific situation when you're off by just 1 oxygen. We saw that 5 was not good enough, too low, and we saw that 6 was too high. So what's between 5 and 6? 5.5, 5.5 oxygen molecules. So let's recalculate. 2 times 5.5 is 11. 11 plus 1 equals 12. Now everything is balanced. So that's great, but we now have a new problem. I can't have a fraction of an oxygen molecule. You can either have 5 or 6. You can't have 5.5. So here's the second part to this trick. To get rid of this 5.5, multiply everything by 2. Now I have 2 of these. 2 times 5.5 is 11. 2 times 4 is 8. And 2 times 4 is 8. By multiplying everyone by 2, I've gotten rid of that half coefficient. Let's recalculate now. 2 times 4, 8 carbons, 16 hydrogens, then 2 times 11 is 22, plus the 2 oxygens from here means 24 oxygens. Over here we have now 8 carbons, 16 oxygens from here, and 8 oxygens from here. 16 plus 8 equals to 24, and now I have 8 times 2, which is 16 hydrogens. Lo and behold, everything is balanced. So that was my final trick for you. In some instances, it may be easier to use fractions to balance the equation. However, your final answer must only contain whole numbers in their lowest ratios, so in the end, you can just multiply everything by 2. Now, I'm sure many of you are looking at this thinking, what the heck? How the heck did he know to do this? The answer is, I didn't. I'm not smart enough to come up with this by myself. But someone showed me this trick, and now I can apply it to other situations. And now that I've shown you this trick, it's fair game on a test. So when it comes to balancing equations, practice makes perfect. And let me tell you, I've got a lot of practice for you. Now the answers are at the bottom. Please check your answers to make sure you're correct. There's no point in doing all 22 of them only to realize you were wrong the whole time. You'll notice that in the answer key down here, I put 1s in the answers. It's not necessary to put a 1 coefficient. Remember, if you leave it blank, it's assumed to be a 1. I just put the 1 down here as a placeholder so you would know it's the second number or the first number, or whichever number happens to be for the coefficients. Alright, give it a try. Good luck. If you have any questions, come see me. In our next video tutorial, we will discuss different types of chemical reactions.